Ever wondered how AI knows when it's wrong? Like, how does a self-driving car realize it's seeing a rare animal instead of a pedestrian? Or why a medical diagnostic tool might flag a scan as unusual? Today, we're diving into a cutting-edge method for out-of-distribution detection, how AI systems spot data that's outside their training experience. It's a bit of a math-heavy topic, but I'll break it down with simple analogies and real-world examples. Let's go. So here's the problem. AI models are trained on specific data, but the real world is full of surprises. Imagine a model trained to recognize cats in photos. If it sees a cartoon cat, a sketch, or a cat wearing a hat, it might still guess cat. But what if it's completely wrong? That's where out-of-distribution detection comes in. It's the AI's way of saying, this doesn't look like anything I've seen before. Maybe I shouldn't trust my answer. The research we're looking at tackles this by comparing three clever techniques: MSP, RLog, and MDS. Let's break them down. First, MSP, maximum softmax probability. Think of it as a confidence meter. When a model sees an image, it spits out probabilities for each possible class, like saying this is 90% a cat, 8% a dog. MSP just takes the highest number. If that number is low, the model is unsure. But here's the twist. The paper shows this simple metric is mathematically optimal under certain conditions, like when the model's confidence scores are calibrated, meaning they actually reflect real probabilities. Next, RLog, ratio of logits. This one's a bit trickier. It compares the top two predictions. If the model is torn between two classes, say, cat and dog, RLog measures how confident it is in the top choice versus the second. The bigger the gap, the more certain the model is. And guess what? Under specific assumptions, this ratio also becomes a super reliable indicator of uncertainty. Then there's MDS, Mahalanobis Distance score. This one uses geometry. Imagine your data lives in a high-dimensional space, like a map with thousands of axes. MDS measures how far a new data point is from the known regions the model has seen. If it's too far, it's probably out of distribution. The math here gets complex, but the takeaway is simple. This method works exceptionally well when the data follows certain statistical patterns. What makes this research stand out? It doesn't just propose new methods, it proves why these techniques work. The authors show that under realistic assumptions, like models being calibrated or data following specific distributions, these methods are mathematically sound. But here's the kicker. They also test them in real-world scenarios, like medical imaging and autonomous systems, proving their practical value. Now here's where it gets really interesting. The paper introduces a novel approach called KNN density estimator. Think of it as a mathematical detective. Instead of just looking at how close a data point is to its nearest neighbors, KNN compares distances to correct predictions versus incorrect ones. If a data point is way closer to strange examples than familiar ones, it's flagged as out of distribution. Let me put it another way. Imagine you're at a party, trying to guess if someone is a guest or a stranger. The KNN method is like checking how close this person is to the people you know, the correct set, versus strangers, the incorrect set. If they're way closer to strangers, your brain goes, wait, that doesn't make sense. And that's exactly what KNN does, but with numbers. How did they test this? They used a model called DistilBERT, a lightweight language model trained on massive text data. Instead of using the final output, they pulled features from the penultimate layer, the model's final thoughts before it generates an answer. Then they tweaked parameters like lambda, which controls feature emphasis, and k, how many neighbors they compare. All of this ran on a single NVIDIA A6000 GPU, a powerhouse for handling complex language tasks. The results? They show how these methods outperform traditional approaches in detecting anomalies, from medical scans to autonomous systems. But the real takeaway is deeper. By grounding uncertainty estimation in solid math, we're building AI that's not just smart, but aware of its limits. And that's a game changer. So next time you see an AI make a strange prediction, remember, it's not just guessing. It's trying to tell you, I don't know. And that's the first step toward building systems that are truly reliable. Thanks for watching, stay curious, and keep exploring the frontier of AI.